Hello everyone, welcome to the video lecture series of Z transforms. I am Professor Mayur Gohil. In this video lecture I am going to discuss one of the standard formulas but a non-trivial formula. Let us see the formula first. The formula that we are going to find is for Z transform of f of k, where f of k is n plus k choose k, where k is greater equal 0. How to handle this? Let us see. First we write the sequence general term that is given to us, that is f of k. Now since k is greater equals to 0, we have immediately changed our function. Instead of n we are taking k. Okay, so our definition that we will use would be Z transform of f of k, where k runs from 0 to infinity, f of k plus f of k times z to the power minus k. Okay, because our runner is k, we are using this form of the definition. Now what do? We substitute the general term in the series. When we substitute here the general term in the series, what is the next process that will be required? Now we need to understand how to handle this. So what we see here, when k is equals to 0, what happens to the coefficient of z raised to minus 0? It becomes nc0. Okay, so this is what we are going to get. So how do I get this step? Let me explain you. Here what happens is, for each value of k we go on writing the terms that we get. So first, when you put k equals to 0, the first term you will get is n plus 0 c0, which is nothing but nc0, which is 1. That is why the 1 is over here. The next time when you substitute k equals to 1, you get n plus 1 c1 z raised to minus 1. Similarly, n plus 2 choose 2 z raised to minus 2, and so on. Okay, so like that you get the terms. Now let us understand what happens to each of these coefficients. Each of these coefficients, like n plus 1 choose 1, when I take, I can write using the formula. The formula for NCR is n factorial n minus r factorial r factorial. This is the formula. So when you use this formula, it is n plus 1 factorial divided by n plus 1 minus 1 factorial, and then there is 1 factorial, which is n plus 1 into n factorial over n factorial. So you get n plus 1. Okay, that is what you are going to get. Now when you do for n plus 2 choose 2, the same thing happens. N plus 2 n plus 1 into n factorial divided by n plus 2 minus 2 factorial 2 factorial, which is n plus 2 n plus 1 divided by 2 factorial. So this thing, when you see, like, you can generalize this. That is, when there is the fourth power, you will have n into n plus you will have n plus 4 n plus 3 n plus 2 n plus 1 divided by 4 factorial. So you can generalize this up to n, as many as terms you want. So on simplification you get this. Okay, so this is what we get over here. Now we go for the next step. So I'm writing this step again. In the this same step I'll be taking up into the next slide. Okay, so these are the terms that you get. Let us go ahead. Now in the RHS you have the terms, and in the LHS I have written, instead of f of k, I have written down the function, because at this step you can see there is no k in the uh, RHS. Okay, so I don't want to lose the sight of what my original function, original sequence was given, so I'm keep it on the left hand side. Now I see that these are the terms that I have. How to handle them? What I do a very important adjustment. I can see that in each of the coefficients over here, n plus 1, and then here also n plus 1, then there is n plus 2, then there is n plus 2, then there is n plus 3, everywhere. But in each of them, I can see n plus 1 is already inherent, right? So what I'll do the substitution of put n plus 1 equals to m. When I do that substitution, I get the following expression. How do I get? 1 remains 1, then n plus 1 has become m. Okay, so here this is m. The n plus 1 has turned m, n plus 2 will turn m plus 1, then here n plus 1 has turned m, then same, and then n plus 3 has turned n plus 2. Okay, all you can see, and then n plus 4 has turned m plus 3. Okay, now one more very important adjustment I can tell you. What is the next adjustment that is required is this. Now this, the next step is very important, I would say. Very important step. This step, in this step what I have done is, wherever the odd terms are there, or if you see that z raised to minus 1 is there, I have written this z raised to minus 1 in the as a, like I have made its coefficient to be positive, so I have written this term in the denominator. And what I have done, the next thing is, for the terms where the powers are odd, I have split the plus sign, as plus is written as minus and minus. Okay, so here this plus has become minus here, and then that has changed minus over here. For even terms you need not bother. Only thing is that you write it 1 upon z square. And here this you can write, here this you can write as 1 upon z raised to 4. Not a problem. For this term z raised to minus 3, I have written here it as, the plus has changed, one minus here and other minus is here. Okay, I've done that adjustment. Now if we recall our negative binomial expansion, this is exactly that. Okay, so this is nothing but the negative binomial expansion over here. So I write here the series is for negative binomial expansion. Okay, due to negative binomial expansion. Now this negative binomial expansion, I can club up and write it in a closed format as this way. Okay, so that is 1 upon 1 plus, and the term that is, instead of x I have now minus of 1 over z, so I write that to the power m. And the condition that we had, that the x should be less than 1, so here the condition is the mod x should be less than a, right? So here the condition is that 1 upon z is less than 1. Okay, even if you take minus, that's mod is going to take care of that. So this is what you have. Now in the next step, since we had started with n, and we did the we did the substitution of n plus 1 as m, so we would need resubstitution over here. So we do the resubstitution, put a resubstituting m equals to n plus 1. So we get our final answer. The final answer for z transform of n plus k choose k is 1 upon 1 minus 1 by z to the power n plus 1. This will be our final answer. I hope you have followed this um, example or followed the formula. It is slightly non-trivial because you are not used to negative binomial expansion. Negative binomial expansion is extremely important in coding as well as sequencing formations and other stuff. So, and it is one of the very advanced formulas in counting. Okay, so please go through that video lecture as well as the z transform of n plus k c k that we have dealt right now. Please like the video, share it with your friends. Please let me know your comments in the comment section. I would really appreciate them. Subscribe to my channel. I shall soon see you with the next topic of z transform in the new video lecture. Till then, keep solving good amount of mathematics. Thank you.